the following. And this is for problems 40 through 43. Okay, that's the problem stated, and you're going to classify as A true or B false. Okay? And the statement, the first one is number 40. The volume of the products is 6/8 times the initial volume Okay, now what am I going to use to answer that? Some guy's law was in our definitions from the first day. I'll give you a clue. His first name was Armando. Armando Avogadro. I love Italian names. They are just so beautiful the way they come off the tongue. Armando Avogadro, his law. And what was his law? Equal volumes of gases at equal temperatures and pressures contain equal numbers of molecules. So then, since the mole is just a number, I can use what sort of ratio of volumes am I going to expect here? If I have 6 volumes of water and 5 volumes of water, that would be 11 volumes towards, and this is 11 to 9. So actually, there exists a 11 to 9 ratio. Therefore, is this statement true or false? It is false, yeah. It's false. So it's B. Does everybody see that? Is there anybody who does not see that? It's so straight up, it's sometimes hard to see. You don't see it? Okay. There's 6 volumes of water. They're going to have whatever the volume is. I don't care what it was. A gazillion liters or just a microliter. Doesn't matter. There are going to be 6 of those volumes. Plus 5 volumes, because there's 6 moles of water and 5 moles of carbon dioxide. 6 and 5 is 11. And that's the ratio, that's the volume. There's 11 volumes of products for every 8 volumes of oxygen and 1 volume of pentane. So 8 and 1 is 9. So it's 11 volumes of product gas for 9 volumes of reactant gas. So if I maintained 1 atmosphere the whole time and the reaction went completely, 100% to completion, then I would see the volume increase slightly. And the ratio of the volume of the products to the volume occupied by the reactants at constant pressure and temperature would be 11 to 9. And not 6 to 8. Okay? Is that straight up? It's so simple, it's scary. People like to make it more difficult than it is. Particularly when you're taking a test. You freak out. You know, it can't be that easy. You have self-doubt. That enters in from back. There's a self-doubt on this shoulder. Oh, no, it can't be that easy. I see it all the time. People erase the right answer and write in the wrong one over it. Self-doubt. Don't doubt yourself. This is that straight up. That's what was so great about Avogadro. That's why we named the number after him. Okay? His hypothesis was a powerful tool. Now, so are there any questions about that? Has everybody got it? Okay. Let's move on to question number 41. There's a wealth of information contained in just a simple balanced equation. 41. There are 30 CO2 molecules produced for every 6 pentane molecules consumed. Okay. Does that ring true? How would I know? Well, I got it in a balanced equation here. If I have, so let's just work on scratch paper to make sure. But if I have 6 C5H12, and the balanced equation gives me 5 carbon dioxide, or 6 moles, 6 moles of C5H12. And there are 5 moles of CO2 for every 1 mole of pentane, C5H12. That equals 30 moles of CO2. And so, indeed, that statement is, it's true, right? Therefore, A. So that one is true. Okay, now we're down to 42, which is the magic number from the Hitchhiker's Guide to the Galaxy. Is everybody clear on that one? That was so easy it hurts. I want everybody to nail this question. There's going to be a series of questions just like this. It's not going to be this question, but there'll be similar questions on the actual test. This is, again, the test is not going to turn out to be that difficult. It's just going to be long. And with the practice, you should nail it. Okay? So I can erase this and move to the next one, right? Okay. Okay, 42. Okay? Now, again, okay, the question stated, or the statement says there are 108 grams of water. I give you the molecular weight produced for every 72.15 grams of pentane consumed in the process. So again, this is a straight up dimensional analysis problem given the balanced equation. So what do I want to start over on the left-hand side to figure this out on my scratch paper? Yeah, let's start with the grams of pentane. 72.15 grams of pentane. And there is 1 mole of pentane for every 72.15 grams of pentane. You could have done that one in your head, but I like to write it down just so you got it clearly stated. And now, the next part of this is what? I want the mole ratio. There are 6 moles of water for every 1 mole of pentane. And last but not least, I want to convert that to what? Grams of water. There's 18 grams of water for every 1 mole of water. So this turns out 72.15 divided by 70.15. Okay, yeah, that's 1. 6 times 1 is 6. So I need 6 times 18. So on my scratch paper I go 18, the whole thing's on scratch paper, times 6. 6 times 8, 48. 1 times 6 is 6 and 4 is 1 times 6 is 6 and 4 is 10, yes. See, I'm getting dingy. Sorry about that. So that's 108 grams of water. So, is that statement true? Yes, indeed it is. Therefore, it's going to be another true statement. And now for the last in this series, are there any questions about this before I move on? Straight up, it's just dimensional analysis. Oh, do you need to zoom in on something? Okay. It's just straight up dimensional analysis. And if you just take your time, you're going to work all this out on scratch paper anyway. The numbers shouldn't be the problem. Okay. Okay. Now, oops, I erased that. I shouldn't have done that. What was it? C5H12. Now for the last in the problem, which is 43, and this is a limiting reagent question. And the nice part about this, which I wrote it deliberately to illustrate this fact, you can find the limiting reagent without reference to either product. You can simply look at the reactants. There's enough information contained there. If I just tell you how much of each reactant is present, you should be able to tell me what the limiting reagent is. And that's based upon the simple principle of how much of this reagent is needed to completely consume that reagent given this balanced equation. And so the question is 43, if 144 grams of pentane are used with, I could have said is used, would have probably been better English, is used with 320 grams of oxygen, then O2 is the limiting reagent. this is, again, straight up. So what I'll do is, I'll start with 144 grams on the left-hand side. And now, what do I need to go from grams of pentane to what? Moles of pentane. There's 1 mole of pentane. And it's for every 72 point whatever. What was it I said? Oh.
415.
Okay, I've got. Oh, let's just say 2 grams of C5H12. And now I'm in moles of pentane. I need to go from moles of pentane to moles of what? Well, the question asks me about oxygen, doesn't it? So I'm going, how many moles of oxygen are there? There's 8 moles of O2 for every 1 mole of pentane. And now that I'm in moles of oxygen, I want to go from moles of oxygen to what? What? Grams of oxygen. And there turns out to be 32 grams of oxygen for every 1 mole of O2. 16 grams per atom, so 32 grams per mole. Okay, now, this is again a straight up mathematical calculation. I've got 144 divided by 72.2, which is 2. 2 times 8 is what? 16, so I have to multiply 32 times 16. 2 times 6 is 12. 3 times 6 is 18, 19. And then 32, 2, 9 and 2 is 11. 3 and 2 is 512 grams of O2 are needed. So I would need to have, if I wanted to completely consume all 144 grams, so that's the conceptual part, if I want to consume this completely, that's going to require, so let's write that out here, equals 512 grams of O2. This is all on scratch paper anyway. Turns out there was only 320 there. What does that make oxygen? We've answered the question. We didn't need to refer to either of the products. In the question we did at the end, which is a limiting reagent question, we referred it to the one that I was going to be asking about the theoretical yield of. And so that was what led us to the approach we took. But we can approach it from any point of view. The limiting reagent is definitely going to be revealed by a simple analysis of the reactants themselves. Yes, what was your question?
How did you get 32 grams as equal to 1 mole?
Because what's the atomic mass of oxygen? 16 grams. And there's 2 oxygen atoms. Oxygen is a diatomic molecule, so 32 grams per mole. Okay? Any other questions? Okay, well, I'm sorry to see you all leaving. Was it something I said? I think people are getting tired.
Yes.
We're almost done. Okay, the true-false is next. Actually, the next parts are going to go rather quickly, but I think it'd be best if we took a slight break because people are seeming a little tired. Unless you guys want to try and run through the rest of this without a break.
I'd rather run through it.
You'd rather run through it?
Almost done.
Okay, let's go for it. I'm game. But I am going to eat. Okay, that's a wrap for that question. I am going to